Welcome. Welcome to the series of video lectures on electrostatics, paper 5 of BSc. Till previous classes, we discussed about the introduction to electrostatics, various concepts to be covered, various concepts like electric field intensity, Coulomb's law, electric lines of force, what is charge, what are the basic properties of charge, what are the methods of charge, electrification of charge, and these various points we have discussed in the previous classes, as well as we also discussed about the Gauss law. What is Gauss law? Where do we apply Gauss law? Why Coulomb's law fails to apply? So Coulomb's law is applicable for we can find electric field intensity for point charges. We can find the electric field intensity for point charges using Coulomb's law, whereas we cannot, that is discrete charges. Discrete charges occurs in ultimate individual, those are nothing but the individual charges. So that at that point we can apply Coulomb's law and find out the value of the electric field intensity at that point for the point charges. But for continuous charge distribution, Coulomb's law cannot be applied. So the extension for that is Gauss law. So according to Gauss law, we also discussed that for a enclosed surface, the total electric flux through a closed surface is always equal to 1 by epsilon naught times the charge enclosed by the surface. So the surface may be that must be closed, but it may be symmetrical or asymmetrical. But when the closed surface is symmetrical, we can apply Gauss law very easily for symmetrical bodies, symmetrical closed surfaces, because Gauss law, we assume a Gaussian surface, and hence it is easy to find out the electric field for symmetrical charge distributions. So here we have also dealt about Gauss law and one of the applications to infinite long charged conductor. Now we shall see some more applications of Gauss law. They are to infinite conducting sheet of charge. Now in order to, we are applying Gauss law to all the one-dimensional, two-dimensional as well as three-dimensional surfaces here, or the closed surfaces. So yesterday we dealt with infinite long electric field due to infinite long charge distribution. Now today I am dealing with applying the Gauss law to find the electric field due to infinite conducting sheet of charge. Here, as shown in this figure, this depicts a two-dimensional plane. The positive charge is accumulated on one surface and it is a conducting sheet. Now the charge density is sigma. What is sigma? We dealt with this also previously. Sigma is nothing but the surface charge density. It is the charge per unit area. Now if sigma is the charge density of this conducting sheet of charge Q, then we assume a Gaussian surface to find out the electric field due to this conducting sheet. Now as shown in the figure, the cylindrical surface with curved surface as well as two ends is a Gaussian surface I assumed over here. So we need to find the electric flux through this Gaussian surface, Gaussian cylindrical surface at the both ends of the cylinder as well as the curved surface. Now here I have not shown the point over here. I assume a point E at the extreme right end. We are assuming a point P at the extreme right end. At point P, our aim is to find the electric flux at point P at the right end of the Gaussian cylindrical surface. Now the total electric flux through this Gaussian surface can be sum up for the electric flux at the left end, for the electric flux in the curved surface, for the electric flux through the right end. So here the left end there is no charge, so there the electric field is 0. Now at the extreme right end where we are assuming to find out the electric flux, the charge is the electric flux is, for example, the electric field as well as the surface, infinitesimal surface I am assuming over there as a small surface ds, both are acting in the same direction. Now I can find out, and moreover at point on the curved surface I can say that the electric flux, the electric field intensity as well as the area, infinitesimal area ds, both are acting perpendicular to each other. As well as, then now you can find out the electric flux through the curved surface, through the whole surface. First of all, if you consider the through the total Gaussian surface, I can say that the total flux is equal to integration E dot ds. ds is the infinitesimal area. If you integrate it along the total surface area of the left end, I can integrate it as integral E dot ds. Here I have written is right end, okay, coming from this side. So right end it is integral E dot ds, and curved surface integral E dot ds, and it is for left end integral E dot ds. If you sum up all these three, we just now discussed that at right end both are acting along the same direction. Therefore I say that E dot ds is Es cos E ds cos 0. Therefore it is electric flux at the extreme right end is E into S. Here S is the total surface area of the right end. Then at the curved surface both are acting perpendicular to each other. Therefore I can say that there the electric flux is 0, and the extreme left end there is no charge over there, and hence there is no electric field over there. Therefore the electric flux at the left end is 0. Now the total electric flux is found out to be E into S. Now according to Gauss law, I can say the total electric flux through any Gaussian surface is always equal to 1 by epsilon naught times the charge enclosed by the surface. Therefore I can say that it is Q by epsilon naught. Again I can say just now we have discussed that if sigma is the surface charge density, then the sigma can be written as equal to Q by S. Q is the total charge and S is the surface area, then where the charge is accumulated. Then I can say that Q is equal to sigma S. So there I have written as ES as equal to sigma S by epsilon naught. So it is therefore I can say that the electric field E is equal to sigma by epsilon naught. That is equation number 2. conducting sheet, if the sheet is conducting totally, then I can say that if I assume the Gaussian surface to be like this in the shown in the figure, here you can see the electric field. Electric field in the first surface at extreme left end, I assume that area as ds1. So the infinitesimal area, small area ds1 and the electric field intensity both are acting in the same direction. Therefore there the electric flux will be Es, and at the extreme right it is E ds4. So it is acting, both are acting in the same direction, that therefore it is the ds4, E ds4 integration. So and on the curved surface the areas on the extreme left I have shown it as ds2, and extreme right I have shown it as ds3. So the total electric flux through this Gaussian surface is phi is equal to integral E dot ds1 plus E dot ds2 plus integral E dot ds3 plus integral D dot ds4. Now the curved surface, the electric flux is 0 because electric field and the electric flux both are acting perpendicular to each other. Therefore there is the ds2 across ds2 and ds3, the electric flux is 0. So it is only the flux is contributed only through the surfaces of the cylindrical Gaussian surface. So I can say that the electric flux is equal to Es plus Es. So if it is ds, in order to have avoid the confusion, I have written as S1, S2, S3, S4, no matter, that is ds, ds, you can say take it as ds also. So in order to have to avoid ambiguity, I have written like that. So it is ds1 is, it's anyhow integration of ds1 is S and integration of ds4 is also S. Therefore I wrote it as 2Es. So the total electric flux through the Gaussian surface is phi E is equal to 2Es, and so we also know that according to again Gauss law, it is 1 by epsilon naught Q by Q. So it is Q by epsilon naught. So the total electric flux 2Es is equal to Q by epsilon naught, and E is equal to Q by 2S epsilon naught, and Q by S we know that it as equal to sigma. So sigma is the surface charge density, therefore the electric field intensity is equal to sigma by 2 epsilon naught. So this is one of the second application of Gauss law we are going through, and the next application is applied to three-dimensional figure. It is a sphere. So now the third application is to find the electric field due to a uniformly charged sphere. So here let us consider a sphere. Here our sphere is shown in black, and the Gaussian surface is assumed around it, and it is shown in dotted line. So the dotted sphere is Gaussian sphere surface, whereas the black one is the R sphere, charged sphere of assumption. Now you have to find out the electric field due to this uniformly charged sphere. Now for that we are assuming the sphere of radius capital R. Sphere A is assumed to be, and its center is O, and here we deal with three cases wherein we have to find out the electric field at a point outside the charged sphere, on the charged sphere, and inside the charged sphere. So here three cases arises to find the electric field due to this uniformly charged sphere, and remember that here the charged sphere is a solid sphere, and I am not speaking about the halo sphere. The electric field will be different for halo sphere. Now this charged sphere is A now in this figure. It is A. The center of the sphere is assumed to be O. The radius of the sphere is assumed to be capital R. Capital R. And this sphere is, the charge is plus Q. So it is enclosed with a charge Q. The charge distributed over this sphere is Q. Now we are interested to find out the electric field at a point outside the charged sphere. Now for that I am assuming a Gaussian surface around this sphere, around our charged sphere. Now in the figure the Gaussian surface is shown with dotted line, the dotted sphere. Both these spheres are concentric, means the center of the two spheres is the same. Now at a distance r, at a distance small r, I assumed a point P, right? A point P on the Gaussian surface I am assuming. So here we are assuming the total Gaussian surface is shown with a dotted line. Now I am assuming a small area on that Gaussian surface, that is I denoted it as ds, that is shown in the figure with red, and we have to find the electric field intensity due to this small elemental area ds at point P. Now see, here E is directed. How is E? What is the direction of the electric field intensity? It is a vector and it is directed along the outward normal. It is directed outwards. So for small Gaussian surface, just now I have said, we are assuming a small Gaussian surface of area ds on the dotted Gaussian sphere, right? So this ds is also directed radially outwards. So the direction of the electric field intensity and the direction of the small elemental area ds both are in the same direction. So for this small Gaussian surface, let us find the electric flux. We know what is electric flux. Electric flux is E into ds. E dot ds is electric flux. So here to calculate the electric flux, so E dot ds is equal to E ds. The angle between E and ds is 0, therefore it is E ds cos 0, and that is E in E ds. Right? Now the total electric flux through, if you calculate the electric flux through a small elemental area, we need to integrate it for electric flux through the total Gaussian surface or entire Gaussian surface. You have to find out the electric flux by integrating this E ds. So the electric flux phi E is equal to integral E dot ds, that is equal to E. E is taken out because the electric field intensity is uniform. It is uniform and there is no change in the electric field intensity at any point. Therefore, the electric field intensity is taken out and we are just integrating integral of ds. So, E into the surface area of the sphere is 4 pi r square, that we have written. So, the total electric flux through entire Gaussian surface is given by E into 4 pi r square, that is shown shown with equation number 1. Now again we are applying Gauss law for these all cases, and hence we apply according to Gauss law. So application of Gauss law can say that the electric flux is 1 by epsilon naught times the charge. Therefore, the electric flux which is found out when the point is outside the sphere of assumption, so where you have to find the electric field. So that is found out to be, the flux is found out to be E into 4 pi r square. Therefore, I have written as E into 4 pi r square is equal to Q by epsilon naught. So the electric flux is E into 4 pi r square, and that is equal to Q by epsilon naught. Therefore, the electric field intensity E is found out to be 1 by 4 pi epsilon naught Q by r square. And the units of the electric flux are Newton per Coulomb, Newton Coulomb inverse. So in vector form, I can write electric field intensity as equal to 1 by 4 pi epsilon naught Q by r cube into r cap. So the second case, here initially I said that we are going to find the electric field intensity at 3 points. At 3 points. One, the electric field intensity you have to find outside the uniformly charged sphere, and the electric field intensity you have to find on the sphere, and electric field intensity inside the sphere, charged sphere. So here if you consider it on the sphere, then I can say that the electric field intensity on the sphere, if it is on the sphere, there is no the Gaussian cylindrical surface will be now on the sphere. Therefore, the r will be, the radius of our sphere r, capital R, will be now equal to, the point has been shifted from outside to on the sphere right now, right? So see this figure. So here P point, now it is shifted to shifted on to this, that means the point is on the sphere, therefore that is shifted on to the sphere, so of radius capital R. So now the point, our point to find the electric field intensity is now at a distance of capital R itself. Therefore this small r has become capital R. Small r has become capital R. Therefore I can say that at point on the surface, the small r become, capital R is equal to small r. Therefore the field intensity is given by 1 by 4 pi epsilon naught Q by r square Newton per Coulomb. Now the third case arises where our point P is inside the charged sphere. Now see, our charged sphere is as it is A only, charged sphere, that is shown with black. Uniformly charged sphere is shown with black, and now the point has been shifted inside. Now our aim is to find the electric field intensity at point, the new point, let me say that it is P prime, this is shown in the figure. The Gaussian surface is now shifted to inside the charged sphere. So the Gaussian surface is shown with the blue dotted line, and our point is P prime, where you have to find the electric field intensity E. So again we are assuming a small elemental area ds at point P, and this ds and E both are acting along the same direction radially outwards, right? So here we are saying that now our point P prime is shifted to a distance of r prime. Let me say that the P prime point inside the charged sphere is now at a distance of r prime, right? Now our aim is to find out the value of electric field intensity at point P prime, which is at a distance of r prime from the center of the sphere. Now the Gaussian surface here is inside. Now see, the total outward flux for this small portion ds of Gaussian surface is E dot ds. So it is E and ds are acting in the same direction, therefore I can say that EDS cos 0, and that is equal to EDS. So the electric field, electric flux through the entire Gaussian surface is given by phi E is equal to integration E dot ds, and that is equal to E integral ds. So that is equal to E into 4 pi, generally 4 pi radius square, but here the radius here is r prime. Inside the charged sphere we are assuming it is r prime. Now let it be equation number 1. So the flux when the point is inside the charged sphere, the total electric flux is found to be E into 4 pi r prime square. Now let us find the total charge enclosed by the Gaussian surface. What is the total charge enclosed by the Gaussian surface? So we know that this Gaussian surface is a three-dimensional one. It is enclosed. The sphere possesses some volume, right? And hence the charge enclosed, I can say that it has the charge density. So here what is volume charge density? Volume charge density rho is given by charge per unit volume. So from that I can find out the value of charge enclosed by the Gaussian surface. So the charge will be equal to volume into rho. Rho is charge per unit volume. So the total charge enclosed by Gaussian surface is equal to volume enclosed by it into charge per unit volume. So that's what I have written. As we know that rho is equal to Q by V, I have written as Q is equal to V into rho, volume into rho. So the volume of the sphere is, if the radius is r, our sphere is of radius, for example it is r, then I can say that it is 4 by 3 pi r cube into rho. Here Q is uniformly distributed over the sphere of radius capital R. So here 4 by 3 pi r cube is general volume of the sphere. So here the radius of our sphere is capital R. Therefore I wrote this rho as equal to total charge by, so this is enclosed throughout this charged sphere A. Therefore I say that the rho is equal to total charge by volume. So charge is Q, and it is Q by 4 by 3 pi r cube. Q by 4 by 3 pi r, Q by volume. Charge by volume is nothing but the charge density, volume charge density, that I have shown here. And the rho can be calculated like 3Q by 4 pi capital R cube, where R is the radius of the charge, radius of the charged sphere. So now charge enclosed in the Gaussian surface. We have found out the charge density for the our sphere uniformly charged sphere of radius capital R. So now we have to calculate the charge enclosed in Gaussian surface. What is the charge? So let us find out. That is equal to charge, again charge is equal to volume into rho, volume charge density. Volume into volume charge density gives you the charge enclosed within the surface. So here also for Gaussian surface, the volume of the Gaussian surface is 4 by 3 pi. Gaussian surface is of radius r prime, that I have shown in the figure. So the radius of the Gaussian surface is r prime, where we have assumed a point to find the electric field intensity. So I have written as it is as equal to 4 by 3 pi r prime cube into just now we have found out the charge density, volume charge density, that is 3Q by 4 pi r cube. So this is equal to Q into, after calculating that comes out to be Q into r prime by r whole cube. So from Gauss law, I can say that total electric flux phi E is equal to 1 by epsilon naught times the charge. Therefore, the Gaussian surface, the electric flux, just now we have calculated in the previous slide, and it is shown as E into 4 pi I r prime square, that I have equated to the Gauss law, that is 1 by epsilon. Here the charge of the Gaussian surface. See, we have found out the charge enclosed by the Gaussian surface to be q into r prime by r whole cube. So that is the charge enclosed by the Gaussian surface. And now the charge is that, and the electric flux is found out to be E into 4 pi r prime square. So the flux is equal to q by q is here in the sense it is charge, the total charge enclosed by any surface. So here it is Gaussian surface. For that surface, the charge is found out to be q into r prime by r whole cube. Therefore, the total electric flux through the Gaussian surface is equal to q by epsilon naught. Here the total electric flux through the Gaussian surface is E into 4 pi r prime square, where r prime is the radius of the Gaussian sphere. Right, and that is equal to 1 by epsilon naught q into r prime by r whole cube. So this is equal to, so after calculation it is shown like this: E is equal to 1 by 4 pi epsilon naught q r prime by capital R cube. Here capital R is the radius of the charged sphere, r prime is the radius of the Gaussian surface when the point is assumed inside the charged sphere, and the point is assumed to be at a distance of r prime from the center of the charged sphere. Now here you can see this, you can have a look over this. So here the intensity is found to be maximum on the surface of the sphere, and here see it varies inversely. The electric field intensity varies inversely with the radius at the when the point is outside the sphere, and the electric field intensity is found to be maximum at on the surface of the charged sphere. So this figure, from this figure we can depict this, the electric field intensity at various points on the charged sphere, various points outside, on and inside the charged sphere. This is all about the applications of the charged sphere. Tomorrow we shall also apply this Gauss law for cylinder. Gauss law for a cylinder, long cylinder, right? So thank you.